In 1995, Microsoft releases its newest computer operating system. Windows 95 instantly becomes a global sensation and sets the standard for personal computing. The same year, the company introduces a revolutionary joystick that drastically changes the experience of computer gaming. With unparalleled precision, it outperforms all other joysticks on the market and goes on to sell more than 6 million units. The technology inside this magical stick is the brainchild of theoretical physicist and master of laser wizardry, Tetsuji Aoyagi. In 1988, Aoyagi establishes Digital Stream Corporation, aiming to make the world a better place through the power of optical technology. The company's high-precision disc inspecting devices for CDs and DVDs are used by manufacturers all around the world. Its optical audio cartridges for vinyl records make use of infrared LEDs to read off music with much more accuracy than conventional cartridges. This optical microscope, produced by a major Japanese manufacturer, can take still pictures of living cells at ultra-high speeds. A boon for medical researchers, the device relies on Digital Stream's advanced laser technology.
Aoyagi-san and his engineers at DSC are really smart engineers, especially in the area of all things optical.
We do all the development here.
Big impressions and smart ideas from a company of less than 20 employees. This time on JTAC, we take a close look at the technology developed by a small company that's become a giant in the field of optical engineering.
Hi, and welcome to the program. I'm Marc Carpentier. Today, we are going to take a close look at revolutionary optical technology developed by a small Japanese company called Digital Stream. The company was founded in 1988 by Tetsuji Aoyagi. After graduating from high school in Japan, Aoyagi went to the US, where he studied theoretical physics at Pennsylvania State University. He then went to work for French electronics manufacturer Thomson. It was while at Thomson that he realized the full potential of light-based technology. He later returned to Japan and founded his own company, wanting to pursue the development of products that could benefit society. Among the many projects he undertook, one quickly led to a business relationship with the world's largest software company, a relationship that has survived to this day.
Dr. Aoyagi established Digital Stream at a time when the market for personal computers had just begun to open up. One of the first projects his company undertook was to develop a new way of interacting with computers.
At the time, the keyboard was the only real input device for a computer. Up until then, we'd normally use a pen and paper to write things down, take notes, or make calculations. And not everyone knew how to use a computer. We wondered whether it was possible to use a pen as a base for data entry.
Aoyagi realized the potential for a device that could input text into a computer by recreating the movements of a pen on paper. Firstly, he attached an infrared LED at the tip of the pen. Two sensors measured the distance between them and the LED to determine the position of the pen. In other words, he was applying the principles of triangulation to computer data input. The device received media coverage in Japan, and it became one of the most talked about new technologies in the industry. The news reached Microsoft. Mike Paul is responsible for hardware design and development at Microsoft. He was on a business trip visiting a partner company in Japan when he was told about the pen.
Vice President of Alps Corporation at that time asked us if we would be interested in taking a look at a new type of input device, was this optical pen. developed by a small company in Japan that was known as Digital Stream Corporation. And we were ready to come back to America. We'd been in Japan for a long time, and I said, well, I'm not really so sure. And he goes, no, Mike-san, you should look at this. It's very, very interesting technology. So Kiyono-san called Digital Stream. They threw all their test equipment and device into a car, came up to the small town of Wakuya in Japan, demonstrated the pen input device. We said, very interesting, thank you very much. We went home.
However, upon his return to the U.S., Paul was stunned when, at a meeting with Bill Gates, he learned about a new development project his boss was putting forward.
We were in a meeting with Bill Gates, and he asked us to look at the possibility of developing a pen-type input device. So I'm happy to take advantage of other people's good ideas, and I don't have to do everything by myself. So I immediately contacted Aoyagi-san and said, hey, guess what? Microsoft wants to develop a pen input device. How can we work together?
Paul returned to Japan to meet with Aoyagi, and the two companies began joint development of the optical input pen. 6 months later, a prototype was produced, but it was never commercialized. Engineers at Digital Stream and Microsoft had determined that the device needed software that demanded processing speeds not yet available in personal computers. However, all was not lost. The technology in the optical pen led the companies to develop a blockbuster product. A revolutionary joystick with outstanding precision and control.
I don't know if your camera can see, but can you look in here? You can see that this is actually a ball. The bottom of the joystick handle is a ball, okay? So here's the ball, and on the bottom of the ball, again, we have two LEDs, okay? It looks a lot like the pen project. And as a matter of fact, when we wanted to make an optical joystick, we went, well, we have a pen, and if we just take it and turn it, we have a joystick. Down here, okay, so sensor 1, 2, 3, 4. And what happens is, if we put a lens or just a hole over the top of this, so the light has to shine through before it hits the photodetector, what happens is this. Imagine this is one of the LEDs on the bottom of the joystick. When the light is centered, all four of these see the same amount of light. But as I start to move the joystick one direction, you see that now more light is falling on this sensor, and light has gone away from here, here, and here. So as we move the joystick around, what the sensor sees in terms of the light spot changes, and we can measure those changes to determine where the handle is in space.
The new joystick had dramatically improved controllability. It was exactly what Microsoft needed to enhance its popular flight simulator computer game.
Original joysticks could only go in X and Y. Okay, we wanted to be able to do things like control the speed of the aircraft. And when you fly an aircraft, you can go down, you can go back, you can tilt this way, you can go this way, but you can also turn an aircraft. And we wanted to be able to do all of those things with a single joystick. And the optical system that we based from the pen was the magic technology that allowed us to actually create what's called a multi-axis or multi-degree of freedom joystick.
This stick uses sensors to detect light moving in space. It has no touching parts or points of contact with terminal resistors, so it's very durable. And since its technology derives from the optical pen, it's very precise and can detect the slightest movements. I think that's why this joystick was a success.
The joystick was so successful, it led to a paradigm shift in the industry. It took gaming to a whole new level and made Microsoft a leader in gaming technology. Microsoft quickly recognized Digital Stream as an irreplaceable partner. The companies went on to co-develop other products that have revolutionized the way we use computers, like the optical mouse that did away with the little ball underneath that only worked if you used a mouse pad and stopped working when it got clogged with dust and dirt. You had to remove the ball and clean it every now and then. Very annoying. Joysticks and mice make use of LEDs, but like any other common light source, light from LEDs scatters. Other devices require a much more focused type of light, like that of lasers. With the use of lenses, a laser beam can be focused to a spot that is only microns in width, and that's why lasers are used for engraving data onto digital discs. This technology demands a very high degree of accuracy. Any defect in the disc would result in a loss of information, and the discs would be rendered useless. A quality control device is therefore critical for manufacturers of digital discs. When Dr. Aoyagi established his company, the compact disc had only recently been invented. At the time, there was no standard device for inspecting the quality of manufactured CDs. Developing such technology was much too costly for manufacturers who quickly adopted a device that Aoyagi had developed.
Engraved on the reflective surface of a digital disc are a number of tiny holes called pits. These microscopic depressions are only a half micron in width. The pits and the space between them are detected by a laser and converted into a digital signal of zeros and ones. Any imperfection in the shape of these pits can lead to a loss of information. This disc inspection device developed by Aoyagi is designed to verify the shape of every single pit on a disc. Here a disc is drawn into position and begins to spin. A blue laser beam is shown from underneath onto the surface of the disc. Its role is to read the shape of the pits. Compared to a household CD player, much greater precision is required here. All intrinsic vibrations must be neutralized, and the components must be perfectly anchored into position to keep the laser beam steady. At the core of this device is the laser component called the pickup. The laser light can be seen here shining through a tiny lens. These are the internal workings of the pickup. This is the aperture the laser beam shines out of. This part is the laser itself. It's made from a combination of various elements that amplify light into a laser beam. The laser beam is directed through this passage to the lens and onto the disc. When it strikes the disc, it reflects back into the device and is redirected toward a sensor. If the pits have been properly engraved on the surface of the disc, the laser light is reflected back in a straight line. But if the engraving process has failed, then the light is deflected. This is how the device identifies defective products. Developing this machine posed a great challenge for the engineers.
Fluctuations in temperature cause changes to the material in the order of microns. Since the laser's wavelength is a mere 0.78 microns, the tiniest fluctuations in temperature can result in errors 1,000 times greater. If we assume the emitted laser beam was my size, then the changes due to temperature would be several hundred meters. That is how much the temperature has an effect on the equipment.
Aoyagi needed to develop a way to keep the laser components from moving under the stress induced from the surrounding structures as they expand and shrink due to temperature changes.
Let's say you have a square optical component. These anchor points will be under stress. The pressure on these points can make the component rotate. It will shift in this direction. However, if we place anchor points here and here, then we can prevent the component from rotating. But then the problem is that we have forces from opposite directions, which causes stress on parts such as the prism and the lens. We had to free the glass from those stresses and find the right kind of adhesive and the right way to lock the glass components in place in order to prevent torque that would cause them to rotate.
Aoyagi and his engineers were stumped. Repeated trials only led to more errors. His ideas worked in theory, but what he needed was practical advice.
We conducted theoretical analyses, but the component didn't perform as expected. We consulted with several other companies who have experience in this field. We asked their older engineers for advice. They have a lot of knowledge and gave us great insight. People with practical experience can answer questions that theorists like us struggle with.
Armed with sound advice, Aoyagi and his team found the solution. They calculated the right positions for the anchoring pins and changed the type and volume of adhesive used to secure the lenses and the prism. It took Aoyagi 2 years to finally produce a digital disc inspection device that worked the way it should. The device went on to become the industry standard. It was adopted and still is in use today by manufacturers around the world.
Dr. Aoyagi's inspection device is also used for DVDs and Blu-ray discs, contributing to the improved quality of today's digital media. Now, surprisingly, his company's latest revolutionary product has nothing to do with digital discs and everything to do with analog recordings. Although CDs have largely replaced vinyl records, vinyl is making a comeback. The music industry has begun producing vinyl records again in response to the growing demand of die-hard music fans. Not everyone likes the so-called artificial sound of digital recordings. Many prefer the warmer, velvety tone of analog recordings. But what does this have to do with Digital Stream's optical technology? Mr. Aoyagi.
Hi, Mark-san. Nice to meet you.
Nice to meet you, sir.
Thank you very much for coming
It's
today.
my pleasure to be here.
I'm welcomed by Dr. Aoyagi's son.
New products
I'm looking forward to
with
Tetsuaki has developed a whole new type of audio cartridge for vinyl records.
and today I want to introduce you our optical cartridge.
Okay.
It looks not so big difference.
No.
On the left is a common audio cartridge called an MC or moving coil cartridge. On the right is Tetsuaki's optical cartridge. An MC cartridge relies on coils and a magnet. The coils are attached to the stylus and move within the field of a permanent magnet. This induces an electrical current, which is then amplified and converted into sound by a loudspeaker. An optical cartridge works with an LED and a sensor instead of coils and a magnet. A screen is attached to the stylus and placed between the LED and the sensor. When the needle moves, so does the screen and its shadow. The sensor perceives the shadow's movements and translates them into a signal, which is then converted into sound.
Normal MC cartridge must have magnetic resistance.
Right.
But our optical cartridge there is no magnetic resistance
I see.
because only watching the shadow.
Right. So that means that the needle is able to transfer the vibration much more efficiently.
Yes, right.
And since the proof is in the pudding, I'm given a chance to experience the difference firsthand. I have to admit, the difference is as clear as night and day. Compared to an MC cartridge, Digital Stream's optical cartridge recreates music with much increased frequency response. The music seems to have more depth, better transparency, excellent channel separation, without sacrificing the warm tone associated with analog music playback, appreciated by so many audiophiles.
The new optical audio cartridge amazed music fans, since there hadn't been any innovation in the field of hi-fi audio for many years. Digital Stream makes 3 types of optical cartridges. Its top-of-the-line cartridge has been deemed the best in the world by a popular audiophile magazine. It's also one of the world's most expensive audio cartridges, with a price tag of $20,000, which includes an indispensable equalizer unit. From digital discs and analog music, Aoyagi's know-how in the use of light is opening up a new frontier in medical research.
Yokogawa Electric Corporation is one of Japan's largest manufacturers of measurement and survey devices. The company developed this high-performance microscope for imaging living cells. The cells are illuminated not by natural light, but by laser light. The device produces ultra-high-resolution images at a rate of 96 per minute, making it one of the world's fastest of its kind. The microscope harnesses technology developed by Dr. Aoyagi, an automatic focusing mechanism. The device was developed in response to requests from pharmaceutical companies wishing to confirm the efficacy of various drugs on living cells. Cells need to be photographed continuously over a period of several days. Keeping them in focus presents various problems.
The thickness of the glass petri dish containing the cells changes with temperature. We needed an accurate unit that could properly keep focus on the cells, whatever the conditions.
In response to the company's requirements, Aoyagi thought he could make use of the laser technology called a pickup he developed for his digital disc inspection device. The microscope has 2 laser light sources, one to observe the cells and another for the focusing mechanism. Because the thickness of the glass of the petri dish is constantly changing due to variations in temperature, the lens has to keep readjusting the focus. For this to happen, a laser is focused onto the upper surface of the petri dish. The light is reflected back into the pickup unit and redirected to one of 4 pre-selected photosensors for different magnifications. The sensors convey a signal to a processor, which calculates the error margin in the thickness of the petri dish. The processor then sends a command signal to the lens unit, where tiny actuators engage to adjust the lens. This feedback process is constantly at work, keeping the cells always in focus. The microscope is now used at research institutes all around the world. One of Aoyagi's current projects is taking place at the Kanagawa Institute of Technology. Takeji Takamura is a chemist involved in DNA research and analysis. Together with Aoyagi and his engineers, he's developing a device that can detect various types of bacteria and viruses. The aim is to make the device compact and portable so that it could be used in the field.
One example is avian influenza. Another is the tuberculosis bacteria found in Africa. If we cannot find the source of the outbreak quickly, a pandemic can result. For that reason, we want to develop a portable device that can be taken and used anywhere.
Different types of bacteria and viruses have slight differences in their DNA. Using markers that bind to specific DNA sequences allows researchers to identify an organism. Here's how it works. Firstly, DNA is extracted from the agent under investigation. It's then cultivated in a process called PCR, or polymerase chain reaction. Next, markers are used to identify the agent. A marker is a substance that consists of a special kind of fluorescent pigment that binds with DNA and reacts to laser light. If a marker does not bind with a given DNA, it moves randomly and separately from the DNA. Markers tend to move or spin especially fast due to their lighter molecular weight. The accelerated motion of the marker disperses a laser beam that is shown through it. But when a marker that binds with the DNA is added, the spinning slows as it becomes heavier. In this case, laser light does not disperse and analysis becomes possible. This is how the technology can detect specific bacteria and viruses.
This is a standard fluorescence polarization system. It's precise but very large. Our goal is to create a device of equivalent performance that's around this size.
To shrink the size of the device, all of the components will have to be miniaturized without compromising precision. Anti-vibration measures will be required if the instrument is to be carried around. In the 6 years since development began, 10 different prototypes have been produced. The most recent one is capable of identifying E. coli with a very high level of precision. Aoyagi and Takamura aim to have it ready for market in 2 years' time. It's a big challenge, but one that Aoyagi takes to heart.
Attempting new things is what researchers do. I believe that's something I have to do. For someone like me, light is just a tool. The skills I need to apply the technology depend on my imagination.
The power of imagination is indeed what drives scientists and engineers to develop products that respond to our evolving needs. From the power of his mind and the creative power of his engineers, Dr. Tetsuji Aoyagi has harnessed the power of lasers and LEDs to light our way toward a better future. I'm Marc Carpentier. Thank you for watching, and goodbye.